sliding window problem. So you're given an array of integers norms, and there's a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers in the window. Each time the sliding window moves right one position by one position, okay, and return the max sliding window. Okay, let's see the example. 1, 3, minus 1. Okay. So how the output comes? Okay, this it gives 3, and this gives 3, and this gives 5. 5, 6, 7. Okay. So for this problem, this is a fixed size sliding window of size k, and I need the maximum of each window. So one way I can think about is using brute force to scan the window each time for the max. That would take the maximum of nk. And I'm thinking about whether there's a better way to get the max value of the window. So I'll think about using a monotonic decreasing deck that acts as the candidate list for the maximum of the window. So the rule is simple. When new element enters, I pop everything smaller from the back of the deck, and those elements can never be the max again because the new element is both larger and will stay in the window longer. So the front of the deck is always the current maximum. So when the window slides, I check if the front of the deck has fallen out of the window. If so, I pop it from the front. Yeah, I think that's the general idea. I can code it up. So I use a deck. Let's call this deck. We have left to record the left boundary of the window. So let's think about this. The right integer is nums, right? And we check if the right integer, before we check the deck, we need to check if deck exists, right? We use well the deck exists, and whether we wanted to check whether the new one is larger than the last element in the deck. So if this is larger or equal to RA, let's think about it. The deck is going to store the indices. So why this deck should store the indices? So the deck should store indices. Because later we need to, when we try to pop, we wanted to check whether the largest value is still in the window. So we store the indices. If this value is smaller than Ri, that means we need to pop it. So we need to pop and after that we have popped everything is smaller than the newly added one, because those cannot be the candidate of the max value. So we have deck append right. So let's think, when are we going to stop in this case? stop if right minus left plus 1 is larger than k. That means we need to pop that value. That means we need to update the DAG as well as update the left pointer. So first we want to see if this value has already been popped. So we check, we will just check if nums left equal to okay, I mean just check if left equal to DAG 0. If it is, that means okay, this is still in the candidate pool, but we are going to pop it. Update pointer. If right minus left plus 1 just equal to k. That means okay, we have just found the value window, and we look to at the max there. The max would be this case max is just the first value in the DAG. Okay, 0. Okay. After all that, we return our result. Okay. Oh. Princesses. Okay, awesome. Time complexity of this one is O of n. And the space complexity for this one, we created extra DAG. So that will be O of k.